In this video we'll talk about the quadratic equation, which is a special type of equation when it comes to variable rates of change. It's just one example of a situation where we will encounter variable rates. Okay, so in a previous video we looked at the idea of comparing 2x plus 1 to taking 2x plus 1 and adding to it this extra term, x squared. Well, what ends up happening, we noticed, is that we have an increase that's constant of 2 whenever we're looking at just 2x plus 1. So we start at 1, up to 3, up to 5, up to 7, up to 9, up to 11, up to 13. But whenever we add that x squared term in there, we are now adding the square of a value, which in essence says that let's take the 2x plus 1 and add to it the square of this value. So 1 plus 0 squared is still 1. 3 plus 1 squared is 4. 5 plus 2 squared is 9. 7 plus 3 squared is 9 plus 7 is 16. So immediately we see that the rate of change is no longer constant. For a 1 unit increase in the input, we go 3, 5, 7, 9, 11, 13. So we notice that the rates of change are changing, and hence we get something that looks like this. So whereas normally this guy has a constant slope of 2 as you follow along this line, these guys have an increase of, a rate of change that is increasing constantly, and all these line segments basically create somewhat of a curvature. So if you were to kind of connect the dots, so to speak, you'd have this nice curve that seems to deviate away from the line, and it seems to do so at a faster and faster rate. So let's take this function up here into account again and try to understand what connections we can make with the actual equation and the meanings of the values in here. So we know that this guy is the slope or the rate of change. We know that this guy is the initial value or the vertical intercept. But what conclusions can we make about the x squared? So let's begin one more time by just taking a look at the differences in the y compared to the differences in the x. So I'm going to create a new column here. I'm going to call this change in y over change in x. Okay, well, the change in x's are all 1, if you notice. 1, 1, 1, 1, 1, and 1. So I know that I'm going to be dividing all the changes in y's by 1. So I'm not even going to write that part out. So my change in y over change in x is 3. 3 over 1 if you prefer. From 4 to 9, the change in y is 5 and the change in x is 1. Here the change in y is 7. Here the change in y is 9. Here the change in y is 11. And here the change in y is 13. Okay, well, what kinds of things could we say? Well, suppose this was talking about miles, and this was talking about hours. So for lack of better example for the moment, let's just say that we're talking about an increase of 3 miles over 1 hour. So if this were 3 miles per hour, that means in 1 hour we have traveled 3 miles. But over the next hour, from 1 hour to 2 hours, we've traveled 5 miles. So we actually went 5 miles per hour. So in the context of a problem, you could think about these as individual speeds, as miles per hour, and miles per hour. So what's happening to the rate of this car? Well, as we saw earlier, it starts off at 0, 1, then it has a rate of change of 3, then a rate of change of 5, then a rate of change of 7 across each additional input. And so the rate of change is getting higher and higher. In other words, this object, whatever it is, seems to be speeding up. Okay, well, we'll add one more thing here. And the thing that we'll add is a new column, which we're used to this idea of a slope, but let's look at the change in the slope. So this might seem kind of weird at first, but let's talk about the change in the rate of change. So sometimes we call this the change in the rate of change, or the change in the slope. So what I'm going to do is I'm going to look at the changes in all of these speeds. Okay, so if this is miles per hour, then over the course of from 1 hour to the next, my speed increases. And how much does it increase by? Well, it increases by 2 miles per hour in 1 hour. So when I went from 0 to 1, and then I went from 1 to 2, over the span of that 1 hour period, the speed increased. Similarly, here, the increase in the slope is 2. 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 So what's my conclusion about the fact that all of these are constant 2's? Well, my conclusion is that the speed of this object is increasing. So the speed is increasing, the slope, by 2 miles per hour every hour. That's what conclusion we can draw about that situation. Well, let's look back at the equation that we were dealing with. Y equals 2x, y equals x squared plus 2x plus 1. Okay, so we know we still have this guy in our table, and we know that 1 is the initial value. Okay, so that means when x is 0, y is 1. So in this situation, what is our x? Well, our x is hours, and our y is miles. So that means that at the 0th hour, in other words, when this object first started moving, it was 1 mile away from whatever we're measuring the distance from. Now 2 can still be thought of as the constant rate of change. That, in other words, this would be in miles per hour. In other words, change in output over change in input. But we notice that the slope is constantly changing. That, in other words, the slope went from 3 to 5 to 7 to 9 to 11 to 13. Well, we can think about this as the initial rate of change. It is basically, so it's no longer a constant rate of change, because we notice that according to our graph, the slopes are always changing. We have curvature to it now. So we call this kind of the initial rate of change, or the blast-off speed. So we can say that at the start, the car or the object moved at a rate of 2 miles per hour. And we basically, as long as we say at the start, we're being pretty accurate. Now, what do we mean by at the start? Well, that just means that right away, right at the blast-off right here, if you think about this as the blast-off point, that object is moving at a rate of 2 miles per hour. Now, because there's so much curvature, it's only moving that fast at takeoff. But we notice right away that the slopes are constantly going up. They're going up by 2 miles per hour every hour. Okay, so where does the 2 come from? In other words, we can see where the 1 comes into play and the 2 comes into play, because we're used to that idea, but there must be something here regarding this term that tells us about the variable rate of change. Okay, well, notice that the coefficient in front of x squared is a 1. We can always put down a 1 in front of a variable. We have 1x squared. And notice that if I were to double or multiply the exponent by this value here, so 1x squared, and I multiply this times this, I would get 2. So if I multiplied the exponent by the coefficient, I get 2. And it just so happens that 2 is my change in the rate of change. So this tells me how much is how much the speed of this object is increasing by. In other words, the object is gaining 2 miles per hour in speed every hour that passes. Okay, now I know this is kind of tricky at first. It's a little bit confusing because we aren't used to talking about a value like this. We can still think about this as the initial rate of change, this is the initial value, but this little guy is kind of throwing us off a little bit. So let's take a look at another example to try to make this a little more concrete. In this next example, let's take a look at y equals negative 3x squared plus 10x plus 4. So we notice that, first of all, I'm sorry, I'm going to change one thing here. I'm going to make this plus 50, and we notice a couple of things. So first of all, we can generate all of these values in this table by using our calculator. The way I will do that is to go to y equals, and I'm going to type in this equation. Negative 3 times x squared, so I can just do actually negative 3x and then the power of 2 plus 10x plus 50. So I could do this by hand. I could plug in a number for x, square it, multiply it by negative 3, plug in that value for x here, multiply that by 10, combine all the terms together, but that's a lot of work. So what I'm going to do is I'm going to set up my table because I want to see the output value. So I'll go to second window. My tables start, I want my x values to start at 0, so I'll have that at 0. I want them to increase, this is the change in table of 1, and I'm going to set both of independent and dependent to auto. Now when I go to second graph, here is the table that I'm actually witnessing over on this side. So it goes 0, 1, 2, 3, 4, 5, 6, and what it does is it takes my equation from y1 in my y equals screen, and based on that it calculates these outputs based on these inputs. So that's how I've generated my table. Okay, well now what we want to do is try to understand the connections between these different parameters in the equation. So we notice that 50 is the initial value. That's the vertical intercept. In other words, in my graph, I would start at the point 0, 50. So that's just as before. Now 10x, again, represents my initial rate of change. In other words, that's my blast-off speed. Okay, well my change in y over change in x, again, notice that in this example that my change in x is always 1. So I'd always be dividing by 1. Just important thing to keep track of. But my outputs are going from 50 to 57, so that's a change of 7 per a change of x and change in x of 1. Then my input only increases by 1 for a 1 unit change in x. Well, what happens next? I have a decrease of 5. And then I have a decrease of 42 minus 53 is a decrease of 9. 25 minus 42 is a decrease of 17. And 25 to 2 is a decrease of 23. Well, let's again take a look at the change in the slope. So is there any pattern in the change of the slope? So in other words, the change in my change in y over change in x. Well, I noticed that my slope went from 7 to 1. So that means my slope decreased by 6 units. From 1 to negative 5, my slope went from a positive number to a negative number, which means it also decreased by 6. This decrease here, from negative 5 to negative 9, is, I think I might have made a mistake, 53 to 42, should actually be a decrease of 11, not 9. That was my mistake. So that means my slope dropped from negative 5 to negative 11, which is a drop of 6, a change of 6 units in my slope. Again, this is negative 6, and this is negative 6. So what does this say? Our rate of change was constantly changing by negative 6. So come back here to this equation and notice that, as in the previous example, if I take the coefficient of the x squared term and I multiply it by 2, I get negative 6. That's pretty cool, huh? So these values here are what's happening to your slope is determined fully by multiplying the coefficient of the x squared by the exponent. So I have the initial value is the point 0, 50. When x equals 0, y equals 50. We know that the initial rate of change, or what we're calling the blast-off speed, is 10, or a 1 unit change in x produces a 10 unit change in y. and the slope is constantly decreasing by 6.